Hi everybody, today's video is on relationships between variables. So the essential question that we are trying to answer today is, when you change one variable, how is the other variable affected? So relationships between variables matter. One of the goals of our physics class this year is to show you that we can use science to be able to explain the past and predict the future based on patterns that we observe. So everything around us is connected to everything else. Physics is not a discrete topic, but it's something that's actually woven throughout your life and our world, and making changes to one variable in the world or in your surroundings can actually have a big impact on other variables around us. So in order to explain the past and predict the future, we need to find out how changing one variable impacts other variables. This connection between two variables is what we call a relationship, and it's the building block of equations. It's important to recognize that equations that we use in science are all based on natural phenomena that we observe. So you can build an equation based on patterns that you see. And we will be working on this in future lectures. But in general, in terms of variables, we want to know if increasing one variable makes the other variable either stay the same, increase, or decrease, and by how much it does. So there are three key terms that I want you to be looking for in this slideshow presentation. The first is no relationship. The second is linear relationship. And the third is inverse relationship. So by the end of this lecture, you should understand what these three relationships look like and how you'd identify them. So there are lots of different types of relationships between variables out there, but we are covering three main ones in this video. The first is when we have no relationship between data. So sometimes variables are unrelated to each other, and changing one has no impact at all on the other variable. For example, if we use the variable of height and a variable being the color of my shirt, my height is unrelated to the color of my shirt. It doesn't matter whether I wear a red shirt to school one day or a blue shirt. My height and shirt color are not related. One does not impact the other. In many cases, when you change one variable, the other variable actually changes as well. And we're going to be talking about two of these. The first is called the linear relationship. And linear relationships are also sometimes called direct or proportional relationships, if you may have heard that in a math class. In a linear relationship, when we increase the value of one of the variables, it increases the value of the other variable as well, and by the same percent. So if you double one variable, the other variable doubles, for example. In addition, in a linear relationship, decreasing the value of one variable will decrease the value of the other variable also by the same percent. So if we have one thing, then the other thing halves as well. So examples may include the number of people in our classroom and the number of shoes in our classroom. If we double the number of people inside our classroom, we have likely doubled the number of shoes that are also inside. Maybe there is a linear relationship between jelly beans, number of jelly beans, and how happy you are. So let's look at an ideal data set that is representing a linear relationship between two variables. Our variables are number of people and number of shoes. So you can see over on the left, when we have one person, we're going to have 2 shoes. And if we double the number of people, so we go from 1 to 2, we are also doubling the number of shoes from 2 to 4. The same can be said if we quadruple the number of people. So we're going from 1 person to 4 people. We're also quadrupling the number of shoes, so from 2 to 8 shoes. As one variable increases, the other variable increases. So that last slide had some really ideal looking data. The relationship between the variables was pretty easy to see. Let's look at some more realistic looking data. Now, it's not as clear if the relationship between jelly beans eaten and level of happiness is linear or not. There's no obvious pattern just by looking at the data table. But we can use a tool to get a clearer picture of what the true relationship between jelly beans eaten and level of happiness is, and this tool is simply a graph. So here's a graph we created looking at the relationship between jelly beans and happiness, but we're going to consider this a bad graph of data. It's not all bad. There are some good things about this graph. It's set up nicely. Along the x-axis, you've got jelly beans, and it's scaled well. On the y-axis, you have happiness, and again, it's in nice increments there. The range is good. The data fills most of the graph. It's not squished all into one corner. What we don't like about this graph is the line connecting these data points, our 4 data points, has no real meaning. This is a common mistake that a lot of people make, is we put points on a graph and we want to connect them all up with these straight lines. When we do this, it doesn't help us to figure out what the true relationship is between our 2 variables, and in this case, our variables, again, are jelly beans and happiness. It doesn't make sense that between 1 and 2 jelly beans, your happiness would go up a whole lot, but then between 2 and 3 jelly beans, it doesn't really go up much at all. So we're going to create a better graph of our data. So we're going to set up our graph with jelly beans on the x-axis, happiness on the y-axis, and plot our points. But instead of connecting our data points with a line, we want to look at what the overall trend in the data is telling us. Is the data going up? Is it going down? Is it curving? And we want to draw a line that represents this trend that we see. Remember, the line does not have to go through all your data points. It just has to represent the trend of what your data is doing. So we are going to draw the simplest line or curve that shows the trend of this data, and this line is called the best fit line. So the simplest possible solution or line that you could draw here is going to the up and to the right of the graph. The reason all those data points don't fall exactly on the line is that when we collect data, there can be errors involved. So a best fit line helps us kind of see through those errors at what the overall general pattern is between the relationships between the variables. And if the pattern that's formed is a straight line, such as this one is, then we call this a linear relationship. So what does the slope of this line tell you? We can see by looking at the graph that for every 1 jelly bean that we eat, our happiness goes up by an amount of 10. The slope of a line is rise divided by the run. So the rise in this case is 10. It's going up 10, and it's going to be written over the run, which is 1. So the slope of our line is 10 divided by 1, which is just 10. In math, you may have made an equation out of this. Since we figured out that the slope of the line is 10, we can write this equation of the line as y equals 10x. X is down here. X is our axis in jelly beans, and happiness is our variable on the y-axis. But we're not writing things in terms of x and y here. We're using the variables that we actually have. So in this case, jelly beans and happiness, and we're looking at the relationship between jelly beans and happiness. So we can rewrite this as h equals 10j. Happiness equals 10 times jelly beans. If j equals 1, then your happiness is 10. If j equals 2, your happiness is 20. So this is one way that we can look at data in real-life relationships and construct equations based on those relationships. The y-intercept in this case is where the line is crossing the y-axis, and you can see here when I have 0 jelly beans, I am completely not happy. I have no happiness. The second important relationship we're going to be talking about a lot in class this year is the inverse relationship. In an inverse relationship, increasing the value of one variable decreases the value of the other variable. So if one variable doubles, the other one is cut in half. The opposite is also true. By decreasing the value of the first variable, you end up increasing the value of the second. So an example from real life of an inverse relationship is the distance you drive. As the distance you drive increases, the amount of gas left in your car decreases. So if we look at some ideal data indicating an inverse relationship, and the two variables we're going to look at here are how number of massages affects the stress level, the level of stress you have. So we start out with 2 massages leading to a stress level of 100. If we then double the amount of massages we receive, okay, we are then going to cut in half our level of stress. So as one variable increases, the other variable is decreasing. If instead of doubling the number of massages, we triple the number of massages, so we're going from 2 massages to 3 massages, our stress level is going to turn into 1/3 of the original stress level. So as one value goes up by 3 times, the other one is 1/3 of what it originally was. So what does this data look like on a graph? So here we have our massages on our x-axis, number of massages, and our stress level on our y-axis. And we've plotted our data points, and you can see that the best fit line for data that has an inverse relationship is actually a curved line. And you can clearly see as the number of massages increases, the stress level is going to be decreasing. In particular, with this data set, when one variable is doubling, the other one is being halved. So we can look at where the line is around 4 massages right here with the red tick, and at 4 massages our stress level is 50. You can look at this point on the line. If we double the number of massages to 8 massages, which would be approximately right here, you can see that the stress level is going to be right at 25. So put 2 dashes there. So we've got at 4 massages, the stress is 50. If we double the number of massages, we are halving the level of stress to 25. Unlike our previous graph of the linear relationship, this graph has no intercepts. So the lines are getting closer and closer to both the y and x axis, but they're not going to cross them. These are called asymptotes. And we may be talking about this in the future in this class. But the takeaway for this slide is that the best fit line in an inverse relationship is going to be a curve. So to summarize, mathematical relationships help us explain the past and help us predict the future in science. So looking at how variables influence each other is a really powerful thing. If 2 variables have no relationship at all, you cannot use one to predict the other. Like the example we used, as the color of my shirt has no effect on my height. If 2 variables have a linear relationship, this means that when one of them changes, the other will change by the same percent. So if one goes up, the other is going to go up. If the one goes down, the other will go down. And in an inverse relationship, when one variable changes, the other is going to change by the reciprocal amount. So as one gets bigger, the other is going to end up getting smaller. So if one doubles, the other one will halve. So in your notes right now, you should have information on what the difference between no relationship between variables is versus linear relationships and inverse relationship. You should also have a little sketch somewhere that has a picture of what these relationships look like when they're plotted on a graph. You do not have to plot the data that we listed in the video, but I would draw a little sketch indicating what the pattern looks like.